Yeah. All right. So I'll start with maybe some motivational slides. Many people interested in hydrodynamics, and all of them have different motivations. I'll want to talk about why physicists are interested in hydrodynamics, and my motivations will be similar to previous talk, although taking somewhat different angle at the same thing. But I mean, before we get there, I mean, so hydrodynamics is a behavior when there is orderly flow on a large scale in a system which microscopically is completely chaotic. And if you think about what's happening here on the atomic scale, there are molecules which behave randomly, collide, and forget very quickly the state in which they started. However, some order surprisingly emerges from that chaotic behavior, and that order, I mean, it's all around us. And I mean, if you've been to the pool, you maybe know what hydrodynamics is and can skip this lecture. But I mean, just to tell you everything that what we all know already. Hydrodynamics describes a very wide range of phenomena and on very different length scales. And as you can see in this picture, everything in this picture, including the wave and the boats and the people in them and the vapor droplets from the water, all of that is guided by hydrodynamics on different scales, and so that's what attracts many scientists to hydrodynamics. For physicists, yeah, that's it again, so that we can all admire. So for physicists, maybe the more appealing thing here is try to understand how the orderly behavior, and I mean orderly, including this highly nonlinear, highly complex, highly elaborate, but nevertheless orderly. I mean, it's not chaotic. Behavior emerges from microscopic laws of physics, and I mean, a dry approach to that would say that we are, I mean, it's guided by symmetries. So if we have fundamental symmetries of space-time, translation symmetry, space and time, rotation symmetry, Euclidean space, mean rotation symmetry, then all of these are continuous symmetries, and they're global, but they result in local conservation laws, and these local conservation laws for quantities which are conserved even after the microscopic chaotic behavior is averaged out, emerge as what guides the behavior on largest length scales in all these very familiar phenomena, and so yeah, so just repeating, following the textbook, basically. So this picture, well understood, of course, and most clearly was stated a long time ago by Boltzmann. And basically, what Boltzmann told us is that there are microscopic correlations that are very quickly forgotten because there is ergodicity emerging from chaotic collisions of atoms and molecules on short timescales. And because of that, all non-conserved quantities are quickly erased from the system memory, and only conserved quantities survive. And then these conserved quantities obey local conservation laws, and that basically is what the minimal description of hydrodynamics is. So somehow it's a combination of symmetry. Usual picture is that it's a combination of continuous symmetries and microscopic chaos, which allows few degrees of freedom to be singled out, and and emerge as the main players on large length scales and time scales. Yeah, so then, I mean, of course, this is a very old subject, starting from a long time ago, and then it's been developed in various ways in 20th century and then in 21st century, and the talk you just heard by Luca is an example of that. But yeah, I think for, am I going forward and back? Yeah. Yeah, so I think for physicists, the interesting question is to actually understand in more detail that construction. I mean, so there is continuous symmetry and there is microscopic chaos, and how microscopic chaos leads to hydrodynamics, and so that's kind of the motivation for the talk you just heard. Then also various interesting questions about what happens if if the sharp separation of length scales and time scales that Boltzmann introduced for conserved quantities and not conserved quantities, if that's somehow lifted or degraded, and then what you have is interesting non-Markovian effects, and you can have a system which is nominally hydrodynamical, but there are certain aspects of it, some correlations or some observables or variables that have long-time memory about things, and this is always interesting, because if you nail this down, it allows you to understand actually very precisely how hydrodynamic behavior emerges in a real system. And so there are many examples of that kind in history of physics. Maybe the most famous one, I'm not sure whether it's known to people in this audience, is the phenomenon in classical gases that was discovered by Dorfman and Co. And this is basically the work in the context of or breakdown of BGKKY hierarchy that was assumed to be like a golden standard for a long time, and then these people discovered that even in classical gas, where Boltzmann told us, what he told us, apparently there is no perfectly sharp separation of length scales and time scale of hydrodynamic length scales and time scales, and for length scale time scales for other quantities. And then after this work, many other examples like that emerged. So Anderson localization probably is most important, because in this case, I mean, diffusion, which is the epitome of hydrodynamical behavior, is quenched in the presence of microscopic interactions with short-range correlation length disorder, and then later they've been interested in other phenomena of similar kind, where there are non-Markovian effect on long-time memory, and the one which is probably more familiar is weak localization, and then more recently medium body localization. And so it's useful to put what we are going to talk about in that context, because the effects in electron fluids that we're going to be interested are of that type. And so it's interesting to put it in this framework. So we'll discuss that, and then also talk about what non-local effects arise and how they show up in kinetic coefficients, and what long-time memory, what we expect for long-time memory, and ultimately how we understand microscopically in terms of various microscopic rates of different processes, and also how we measure it. Yeah, so that's kind of the plan, and I'm going to focus on electron fluids. Basically because that's what I was instructed to do by school organizers. But these questions, I mean, how hydrodynamics emerges from microscopic interactions to large length scales, I mean, it can be studied in other systems. I mean, we'll talk mostly about electrons, and in electrons, just to do that cleanly, In electrons, usually we don't have hydrodynamic picture. If we take a metal, then the main interaction is electrons being scattered by disorder, and in this case, momentum is not a conserved, variable on long time scales, and basically it's simply simple diffusive picture. However, there are certain high mobility electron systems where there is very little disorder, or there are strong interactions, or maybe a combination of both, such as graphene or high mobility gallium arsenide systems, or this systems like that, where mobilities are very high, and then in this case, interaction between electrons, even if they're not too strong, can make electrons collide with each other in a momentum conserving way, and then in the electron system, the same thing will happen as in the air around us. I mean, there are very rapid collisions, but nevertheless, energy, momentum, and other quantities which are conserved because of conservation laws acquire a hydrodynamic status. And so there is interest, in part because these electron systems are now actively studied, also in part because they are much easier to probe microscopically than, let's say, air. That's why there is a lot of interest in these things. Another kind of system where interactions are strong are non-Fermi liquids and strange metals, and so there is also interest in developing a hydrodynamic picture. I think we will mostly focus on these systems because I think for the occasion it is simpler, and also experiments are more active in these three systems, and we'll talk about that. But I mean, there are also other systems, not going to be talked about here, where very similar behavior emerges. For example, if you take cold gases and ask, again, these are systems that can be probed with extreme precision. And so in cold gases, one can ask all these same questions, and there's an entirely new set of tools to probe hydrodynamic behavior in such systems that emerged over the last 10 years. That's another playground where hydrodynamics can be studied, and much of that is already happening, and more will happen soon. But I think we're not going to get into that. So I think this kind of I should also acknowledge that there is a lot of literature. So this is obviously not anywhere complete list. I mean, there are some foundational papers. Let's say this paper where electron hydrodynamics was first introduced, and then some experimental papers. Some experimental papers observing it for the first time, and then also some papers proposing graphene as a platform for hydrodynamics, and many of these people are here. But there are many more papers that are not on the list. Actually, it's a large field and a pretty active one. So, oops, what did I do? So I mean, speaking of graphene, or maybe even before graphene, if there are questions, just stop me and ask any question. I mean, I'm going to use slides mostly for speed. I'm not, switching between slides and chalkboard. Not my favorite mode. So, put all equations on the slides, but I'm happy to talk. Any questions, just stop me. Also because I'm a slow speaker, I think it will be appropriate. The status? I'll let you decide. I mean, I didn't see any signatures of hydrodynamic behavior. If you estimate electron mean free path, it's gigantic. So maybe if they grow samples which are a mile long, they will see hydrodynamics. Quite possible, because their samples are big compared to graphene, which are tiny. I mean, their samples are big. Yeah. Yeah. So I mean, if you take a pure point of view on hydrodynamics, then maybe it is not. But then, for many people, any free electron flow, whether collisions are happening rapidly or not so rapidly, any free electron flow not too much affected by phonons is hydrodynamics. But I mean, I'm not going to talk about it, so I'll let you decide. I mean, graphene and gallium arsenide are much more interesting, and they've been really progress there. Yeah.
Sorry, I think the microphone switch very hard to hear. Microphone.
I think you need to take the microphone further up. They can't hear you.
Ah. Oh, because it fell off. Sure. Sorry about that. Yeah. Thank you. Great. Okay. Yeah. So in graphene, for example, I mean, speaking about graphene, then there is there are three regimes. I mean, if you vary carrier density near Dirac point, then if you are hole doped or electron doped, then you have a Fermi liquid, and there you have Fermi liquid hydrodynamics. And if you are at the Dirac point, then you have a gas in which there are electrons and holes in roughly comparable numbers, and then there is a two-species hydrodynamics due to that. But either way, graphene is an interesting system because it's being atomically thin. It has very strong electron-electron interactions that are virtually unscreened, and no umklapp scattering because of that. I mean, because of the crystal lattice in graphene having special properties, there is no umklapp scattering. Ask me later if you want details. And because of that, collisions are really momentum conserving, and also coupling to phonons is relatively weak. And as a result, I mean, one can see all the things you want to see in electron systems, such as viscous flows and so forth. And that's the one. Yeah. So for the purpose of this talk, I mean, I'll be referring mostly, speaking about graphene, be referring mostly to doping away from Dirac point. Although I mean, everything we'll talk about will be very easy, very natural to generalize. Yeah. Okay. So these are people. Actually, not all of the people, but so it happened that I couldn't find the pictures. These are all the people who did the work on which the talk is based, and actually how you is here. With him, we wrote some of the first memorable and most memorable papers on the subject. Also Grisha and with Sergey and with Patrick, and yeah, actually all of them. Yeah, so these are collaborators and friends, and more than that. Yeah, and many of them are from MIT, and as you can see, it's very easy to distinguish who is MIT and who is not MIT. MIT people are smiling. MIT people are smiling, and Huh? Yeah, no, not all of them. I mean, he's at Stanford. He's at Stanford. No, not all of them at Harvard. No. Yeah. Okay. Good. Sorry. Maybe I. What do you say?
They're smiling because they're leaving MIT.
Not necessarily. I mean, I can tell you why exactly they are smiling. I mean, he's smiling because he's cooking at the moment this picture is taken.
The audience.
He's smiling because he's watching sunset. A rare event in his life. He's watching sunset, and then how you had to smile because there was an official picture taken. But anyway, let's not get into that. Yeah. So anyway, let's talk about more interesting stuff. So why anyone should be interested in electron hydrodynamics? And so here, I mean, maybe I'm too ambitious, but what I want to talk about three topics that I'm now working on related to electron hydrodynamics. I mean, there are other things that I'm doing also related, but no time to talk about it here. Also, we'll have to see how it works out with these three topics. So one is what I was mandated to talk about, which is the viscous flows, electron viscosity, and all of that. So this is like electron hydrodynamics proper. And so let me say a few words about it, in way of introduction. So it is a regime that has been proposed a long time ago, where a counterintuitive behavior emerges, in which carrier collisions assist conduction. So it's an interesting situation where microscopic scattering actually helps conduction rather than hinders it. Unlike phonons and, let's say, strange metal or another metal, with temperature growing, resistance doesn't grow, here it drops. And so this is a most clear signature of also being very clean, strong electron interactions. This is the clearest signature of electron hydrodynamics. Very unusual behavior when increased scattering tuned by temperature assists conduction and suppresses resistance. So from that point of view, it's comparable to other surprising effects that we know of a similar kind, such as motional narrowing in spin resonance, where isolated spin experiences crystal fields and whatnot. But if it's rapidly moving, or if environment is rapidly changing, so apparently there is more noise or more collisions. But instead, as Van Vleck and Anderson have shown and got prizes for that, spin resonance becomes more narrow. Likewise, there is a phenomenon in optics when a resonance is narrowed by collisions. It's called decay, the decay effect, right? So from that point of view, I mean, electron viscosity is a similar surprising behavior, and every new generation rediscovers viscosity and is surprised by the interesting behavior that arises in this in such systems, and more on that later. But I mean, here, yeah, so resistivity drops with temperature. We already said that. And so we worked on that with all of the people that I showed, but most recently with Sergey. And so with Sergey, we studied the non-Fermi liquid T dependence in electron hydrodynamics. Surprisingly, it turns out that resistivity temperature dependence at lowest temperatures is linear. So this cartoon is pretty much accurate to what the real system indeed shows. So it's very different from what you expect from a Fermi liquid, naively expect from a Fermi liquid, which in 3 dimensions would be a T square. And then that's a two-dimensional electron Fermi surface that are doing that. And instead of T square, apparently mandated by Fermi liquid, you get a T-linear behavior. So that needs to be explained, and one can understand that in terms of demographic picture that we introduced some time ago together with How Are You, and then now this is being used to understand this transfer behavior. Then the other thing I want to talk about is actually I should watch. Oh, okay. Yeah. So the other thing I want to talk about is vortices, and so vortices in a high dynamic regime are interesting because when you have a vortex flow, sorry for the picture, somehow it didn't occur to me when I was copying that it's poor quality, but in a high dynamic regime you can easily create vortices, and then instead of like things are for the ohmic flow when current basically flows along the applied field. Here, current can flow opposite to the applied field, and electric field and current can be anti-aligned, and that's interesting. And so I wrote a paper about it. And then recently there was a demonstration of that effect by Eli Zeldov and his group using nanoscale scanning techniques. So this is a group at Weizmann Institute in Israel, and they're pioneers in nanoscale magnetometry, and they used it to measure current more or less in this regime. And they demonstrated that in an ordinary conductor, the sign of magnetic field of the current is consistent with the flow when current and field are aligned. And in this material, where there is a very much like in graphene, current and field are anti-aligned, and you get vorticity induced by current, and so there is that. Then another question that I think is actively on my mind is high dynamic instabilities. I mean, can we? I mean, so this has been the question since the invention of graphene, because it's very clean, mobilities are very high, and can one actually get in the regime which is not only high dynamical but also like very nonlinear, so that we get instabilities or maybe current-driven turbulence or something like that, and so this has been an interesting question for some time. And then recently, I think there were experiments that demonstrate something like that. I mean, so this is an experiment in Manchester under a Gimes group, happened to be a course on that. And then the key players are Roshan and Alexei, and they are not. So this was published in the early days of COVID, but now they all, they all graduated. They have their own labs, and they're continuing this work. So here they found that if you take graphene, either moire graphene or bilayer graphene or some other kind of graphene, you can drive it by relatively low current to the instability point where something interesting happens, and what exactly is happening is now under investigation. But there is some nonlinear behavior. So as you can see, these are experimental data. Linear resistivity, the usual thing you see in multi-layer graphene or in moire graphene, where there is a main peak at the main Dirac point, side Dirac points. And then if you drive current, the nonlinear IV looks like that. I mean, there is if you take dVdI, dissipation rate per current, then it becomes singular at certain current values. And in more recent experiments, which are now going on in several labs, I mean, it becomes even more singular, can jump, can show hysteretic behavior. So there is a lot going on. And all of that can be induced completely reversibly by increasing current and then cycling it back and forth many times. Samples don't burn, so it's kind of magical. And they're pretty low. So these currents are not anywhere where your samples are endangered. they survive very well for months, and you can see that again and again. And now practical people are interested in that and try to make devices out of it. So it's actually, but I mean, what exactly is going on here, I think, is not very well understood. And so that's something that would be interesting to discuss. Yeah, I mean, if we get,
I guess when you say hydrodynamic instabilities, I might think of like Raleigh-Taylor, one of the named after someone.
Well, there are many options. Yeah. So one that would be one. Then in that paper that we published, I mean, there was another approach. Now I have something else in my mind. Well, hopefully we'll get to discussing that.
And but like just this spike in current, I guess naively this could have a non-hydrodynamic explanation, right? Or is that, or would you disagree with?
No, I mean, just judging by pictures, the only thing I can say is that the current is pretty low. So it's in the regime where we don't expect any additional or a lot of additional scattering. So maybe it's hydrodynamical, maybe not. I mean, I think there is no judgment on that. So this is just taken from that paper, and what it shows is that there is a clear threshold in current, and this threshold current becomes low near Dirac point or near side Dirac point and relatively high away from it. And so there is this interesting recurrent behavior. Also, what this shows, this is a Hall effect under the same conditions. And the Hall effect shows is that the sign of carriers, even there was only one carrier sign at low current, you get, when you reach instability, you get carriers of both signs engaged, which means that from the point of view of band structure, let's say if you're doing it somewhere here and you started on the Hall side, you have both electrons and holes. So there is some current-induced repopulation of bands, and the Hall effect shows that very clearly. Whether it happens in the hydrodynamic regime or outside of the hydrodynamic regime, I think that data doesn't tell us, and this paper also, the experimental paper also doesn't make any claims on that. But I think, given that there are all these questions in the field, posed a long time ago, I think it's interesting try to connect it. I'm not sure that's, yeah.
Maybe I missed this, but I mean, what's the model that's being used to calculate these quantities? Like, what are the assumptions?
This is experiment. This is not theory. Nothing is calculated. This is what these guys measured. I mean, what they measured. So it's a device that, graphene hole bar or ribbon in which you can measure longitudinal resistance. And actually, it's not even a bar. It's a pretty wide device in this case. Pretty wide device, maybe 5 micron by 5 micron. And there are contacts attached with which you can measure longitudinal resistance and hole resistance, and that's what you see. You can drive it. You can drive it to some kind of instability by moderate current, and can do it reversibly. The amazing thing is that it doesn't blow up, doesn't burn. It can go back and forth. Yeah, I'm sorry. So axis is okay. Okay, before we explain that, let me explain a single trace. So if you take a device, apply current, measure voltage, then in linear response regime, you just get linear ohmic resistivity, and linear ohmic resistivity does what you expect it will do. It will peak near Dirac point and side Dirac point as a function of carrier density. Now, if you do the same thing as a function of carrier density, as a function of current, let's say sit somewhere here where the arrow points and vary current, then you will see an IV dependence, and that IV dependence is the red line, monotonic voltage versus current. And then if you take derivative, you see that dVdi is singular. So dVdi versus current shows singular behavior, and we can discuss that later if interesting. But to explain the axis, basically, these pictures are assembled from these pictures. Simply take horizontal slice on every picture here, going horizontally is one of these. So constant y would be constant carrier density, and then with constant carrier density you take IV dependency, something like that, and then vary carrier density, and then that's what you see. So basically, these traces are assembled in 2D picture to visualize where these transitions are happening. Yeah. Yep.
Feel free to move on, but I'm just a little confused. I mean, as you're varying density for this Moray system, I'm assuming there is some point at which umklapp scattering can't be ignored altogether. I mean, or is that irrelevant? Like, I'm trying to understand why hydro is relevant at all.
So umklapp between K point and K prime point is never relevant here, because all of that is at carrier densities which are very close to K Dirac point or K prime Dirac points. So you can't really scatter from K to K prime for crystallographic reasons, right? But then there is a Moiré lattice, and you're saying maybe Moiré lattice is a source of Moiré-like umklapp scattering, maybe, but that's what we have here. Yeah. Anyway, I think to finish that motivational part. ChatGPT, looking over my shoulder as I was making the slides, wrote. Oops.
Often emphasizing discipline and perseverance.
I think it's trying to tell me something. Yeah. Sorry about that. It will. Anyway, I wanted to show it to you just because it's funny, and because I think it's nicely done. Except the last line. Last line makes no sense, but I'm sure next time it will come out better. Everything else is beautiful, including physics inside. Somehow it knows what's happening in graphene. And I didn't prompt it. It was what chat said. Anyway, any questions? Okay, let me see how we are. Good. Yeah. Okay. So let me talk about these tomographic fluids. A few things about them, and then maybe talk about other things. So there are several things I want to discuss. So one is that before we even talk about transport, want to understand quasi-particle lifetimes, and then how these quasi-particle lifetimes enter kinetic coefficients, and how these long-time memory effects arise, and non-local conductivity, and tomographic transport, and so this is kind of the plan for discussing it. And let me just start with very basic reminder of quasi-particle lifetimes in Fermi systems, and I'll be talking about sharp Fermi surface. Sharp Fermi surface is something that can be easily understood from Landau quasi-particle picture, and then, as we will see, the most interesting effect in this case is the kinematics of two-body collisions. and the kinematics of two-body collisions is largely insensitive, because this is all about energy conservation and moment conservation. It's largely insensitive to microscopic details, more sensitive to the geometry of the Fermi surface. So for this discussion, we'll assume that Fermi surface is circular or spherical in 3D, and then can discuss generalization later. But if you have a Fermi gas at zero temperature with a sharp Fermi surface, then we know very well from these two people that all the actions is taking place at the Fermi surface, and states which are deep under the Fermi level are blocked from scattering because of energy conservation and two-body collisions. Yeah, so the field states are not in the game, and quasi-particles are particles dressed with interactions that have life on that sharp Fermi surface. And then there is an argument due to Landau that we'll review that in 3 dimensions predicts lifetimes which are 1 over t square, t is temperature. And so basically that means that lifetime can become very long at low temperature when temperature is much lower than Fermi energy. Then, as you know, we'll see that on that scale in 2-dimensional systems, the lifetimes can become even longer. So they can be, you know, they will scale the temperatures 1 over t to the 4th, and so that's you know that's the thing that we discovered a long time ago together with Hao-Yu, but not for all excitations, only for some of the excitations, and so we'll talk about that. And so this so this story I'm going to tell you because I was asked to talk about that, no choice, but and then we'll talk about that and about surprising collective behaviors in these fluids. Because very long time scales, and not for all excitations, but only for some of the excitations, they translate into some interesting physics, right? And so this is a problem of how an electron lives in an interacting system, and maybe I'm not sure, you know, if people here are old enough to appreciate that quote from Lenin, no one else than Lenin. I think Gamov would enjoy it, but Gamov is no longer around. I mean, he used to be faculty here, not escaped Russia a long time ago, and he would surely like it. And if you and then the connection between that and Fermi liquid actually is borrowed from an article of a friend of mine who is a historian of science, and he was interested in how ideas of politics and other things like that, how they affected science and how they penetrated on science. And so he wrote an interesting article in Physics Today that I enjoyed reading some time ago. And so there he made a point that, you know, many effects that we talk about, many names of physical phenomena that we talk about, like collective phenomena and correlated phenomena and all like that, they were introduced precisely at the time where social struggle was going on about 100 years ago, and this terminology entered physics and stayed. And if you look around, you know, you can see that. And then he also goes on to discuss particular developments, including, you know, theory of Fermi liquid. I don't want to get into that, but I mean, if anyone interested, they can share that article with Physics Today from about 10 years ago. Anyway, let's move on. So quasi-particles, yeah, like we said already, quasi-particles, as nicely shown in this picture, are, if you think about quasi-particle, comparing it to a particle or a horse, then quasi-particle would be a horse dressed with a cloud of horses and anti-horses. So it will look something like that. However, according to Landau, they have as sharp Fermi surface as sharp Fermi surfaces as these guys, and so they can be treated in the same way. So there is a notion that kinematics, all the effects, including the kinematics effects that we're going to talk about, can be generalized and applied not only to Fermi liquids, but also to strongly interacting systems. And there were nice papers by Hao Yu recently actually demonstrating that, and I refer you to that. But what I'm going to do today is, just for the sake of simplicity, focus on the weakly interacting Fermi gas picture, with the hope that because the main effects of interest are just kinematics, they'll be going to be applicable more generally. Yeah, so that's the plan. So we are, maybe just to finish the story, unless you'll remember that. Let me remind you Landau's argument for where T² comes from. So T² comes from the following argument: that if you have a particle excited above the Fermi level, and that particle, by colliding with by colliding with another particle, so particle 1 collides with particle 2, and then they scatter to states, with energies E4 and E3, then because of energy conservation, if you change one, you change the other, and then, as discussed in this book from where this picture is taken, the story is that if you think about phase space for decay, just the golden rule calculation of the rate for particle for this process, then you find the phase space for this particle 2 and 3 is proportional to energy squared. Basically comes from this picture. So this is the Fermi level, and this is energy of particle 3, E3, and this is E2. So you see from this picture that phase space is energy proportional to energy, and then that over phase space particle 1, you get a linear function integrates to quadratic function. That's where T² comes from. And then incidentally, I mean, this picture is taken from this book, and it has a mistake. Just stare at it and try to see. I mean, violate some basic physics laws, and I'll let you think of it. But then one aspect what Landau theory does not account for is angular dependence. And in three-dimensional Fermi systems where he was developing it, this wasn't really an issue, because if you have two particles near Fermi surface colliding with particle 1, particle 2, then their total momentum is conserved, and so the momenta states of 3 and 4, they adapt to the same momentum as momentum states 1 and 2. So they adapt, and then momenta 3 and 4 are related but not locked to momenta 1 and 2. And so this angular freedom of rotation actually doesn't make 3 and 4 rigidly correlated with 1 and 2. In 2 dimensions, however, the story will be different, because if you imagine that all of that is happening on a 2D plane, and you have two particles, momentum P1, P2, and they have to preserve their total total momentum in a two-body process, you see that you can't really rotate it out of the plane. So because of that, you see that this kinematics tells you that so long as Fermi surface is taken to be sharp, your particle states don't have a lot of freedom to scatter around. And so in a single scattering, within effects of water temperature over Fermi energy, the angles will not change. And so that turns out to be interesting and worth exploring. And so sorry, where am I going? Yeah, so that's the same picture, but maybe more slowly. And if you first forget about Fermi surface, if you just take two particles which are colliding, then we know very well how to solve this problem. You go to the center of mass frame, and then in the center of mass frame, your collision is head-on and then head-out. And because of that, the momenta of the incoming particles and outgoing particles will have to lie on the same circle, kinematic circle that we know very well from two-body collisions. But now, if you reintroduce Fermi surface, you have to do it on top of a Fermi surface, and then you immediately discover that most of the phase space here is blocked. So this particle one, can scatter within the thermally broadened Fermi surface region, but can't really go deep in because these states are blocked, and because it can go here, then the other particle can go there. So immediately from that picture, you see immediately that in 2 dimensions, these constraints are blocking not only energies is just like Landau told us, but also kinematic constraints are blocking angles, and because of that, there are strong angular correlations. And then if you think about it, you discover basically, as this picture suggests already, that two particles colliding at a generic angle cannot do much. They can't relax their momenta because they have to at low temperatures they have to scatter at roughly the same angles, maybe up to small thermal broadening. And so generic two-body collision in 2D will not produce angular relaxation, and so essentially will not. I mean, collisions will happen, but they will not relax pretty much anything. However, there is a process which is active in 2D, namely it's happening, and it does produce relaxation. This is the process when particles collide head-on. Particles collide head-on, then by the same picture that we just talked about, particles can collide head-on and then scatter head-out at a pretty much any angle, and they're not constrained on doing that. So you see, it's interesting. The generic two-body collisions are constrained or blocked from being efficient. The only kind of collisions which are allowed are head-on collisions, and so these collisions will obviously dominate the kinetics. And then from this argument, you see immediately that if you are going out of equilibrium, if you're exciting states, particle states above outside equilibrium, the odd part of the Fermi distribution, odd under space and momentum space inversion, and the even part will relax very differently, because the even part, let's say if you put some particle here and some particle here, they can relax in one collision by scattering somewhere, and then the odd states, let's say if you put particle here, say if you put some particles here and some holes here, the anti-symmetric momentum distribution looks like particles and holes at the opposite points, then these will not be able to decide, because this particle can only scatter on something here, but here there is a hole, so there's nothing to scatter on. And as a result, the odd parity collisions will have a very different lifetimes and very different scattering rates. So one can, yeah. So that's, again, that paper that we wrote with Hao Yu way back. If you now, do it more seriously, you see that if you think about it in terms of angular surface shape changes, you see that in the usual hydrodynamics, two shape changes that we care about is current and density variation shown here. But then when you are in 2 dimensions, you have more choices, and there will be long-lived odd parity harmonics, odd parity, deformations of Fermi surface, and relatively short-lived even parity harmonics. And then if you do the calculation referring to that paper, rough estimates show that the change in lifetime of these guys compared to these guys is very big. It's a order T over Fermi energy squared. So if these are T squared, then these are going to be T to the 4th rates. Yeah. So these are. I mean, I think we're done with that. Maybe stop for a second and see if there are any. Actually, let me see what's here. I forgot. Yeah, maybe this isn't so essential. Yeah, yeah. So are there any questions? Yeah.
This collectiveness is a vibration of the thermal surface or direct dependent collision of two possible.
It's independent, but so long as we treat out of equilibrium state as a sharp Fermi C with modulated boundary, which is totally fine to do, I think these are equivalent. Actually, let me skip this. These are details of that argument from that paper. If anyone is interested, can talk about that. But I mean, I'm going to present the same thing maybe on a more modern level in a moment, and then maybe I can come back to questions. Let me also show or mention that there is this. I mean, obviously, we're not the first ones thinking about this problem, and this problem has been around for some time, but somehow the literature has taken a different angle. And what people have done for a long time, they were interested in quasi-particle lifetime in 2D. And it was noticed, there is a long list of papers studying it, and I think it's not even a complete list. Many notable people worked on it, that T square, if you calculate self-energy, then instead of T square that you happily get in 3 dimensions, in 2 dimensions you get something different. You get T square log T. I mean, it sounds interesting, and there've been suggestions that maybe that points to some non-Fermi liquid behavior, but I think nothing really happened along this line. However, these papers did see some signatures of some collinear effects, but I don't think they've been explored. What one can ask, however, is is there contradiction? I mean, I'm arguing that these odd parity excitations are very long-lived, and it's T to the 4th instead of T square. And one can ask, where is it here? Why here we just have T square? So it turns out that this is very interesting, and maybe for those who are doing Green's functions on a 2D Fermi surface, something to check. I mean, we checked it in a different way, but let me just explain it in my way. So it turns out that this process has this rate. However, it doesn't the slow process. I mean, the quasi-particle lifetime you can write as a sum of rates for all participating channels, and of course the channels that have high rates will dominate in the sum. So if there are rates like for odd parity excitations that have very low rates, they will not contribute or contribute very little. And that's indeed what happens to this odd parity process. So you simply, they're simply masked for by even parity process, by even parity contributions. So by contributions of these guys. And that's mainly what this result captures, and one can demonstrate it in a different way, as we did in that paper I cited. So self-energy is dominated by fast pathways, rapid decays, and also by near head-on collisions. So this is evident if you write down the diagram, you see that. But it doesn't capture interesting contribution of long-lived extinctions. Has been tested, by the way. I mean, there was a famous experiment by Jim Eisenstein and collaborators where they used ingenious geometry of two gallium arsenide quantum wells where you can tunnel from one to another, and you can tunnel from a Fermi surface on one to a Fermi surface on the other, and then tune Fermi surface relative to one another and use that as a knob. And so they could test and claim there is this paper that they published where they claimed that they saw this T-square log T. And data on that. Yep.
Is it self-energy is not capturing because somehow in the self-energy calculation, the rates add, and so then it's dominated by the...
Yeah, because T-square is larger than T to the fourth, yeah.
But what is the right calculation to do to get the T to the...
I mean, one can do it in a channel resolved way, and then of course you will see T to the fourth. I don't think anyone can do it with Green's functions, but I mean, we did it in a different way.
But somehow one should be able to calculate some physical, observable, and then it should be dominated by T to the fourth.
Right. So one should. This is why I'm showing this. I mean, these experiments sadly are no longer continued, but because this was a while back. But someone should do it in the right geometry to see these effects. Absolutely, it's very interesting. Yeah, I'm happy to talk later.
Good question. What other mistakes is calculation of self-energy?
No, there are no mistakes. I'm not clear. No,
Not mistakes, but physical. It's somehow not capturing the right physics.
Yeah. It's not. Yeah. So I think they misunderstood. I mean, so now the people who are so some of these people are now doing our stuff, and we're in agreement. Yeah. Questions? I mean.
What the basic
In real space. Okay, in real space will not come up today, I'm afraid. I mean, we'll have to wait. But I mean, let me show you what I have, and then we'll talk about the real space picture. Well, actually, one thing I can say now, maybe I can use the chalkboard. So the real space picture is interesting, and you can think about it as follows. I mean, suppose you have a Fermi gas and you injected one test particle into it, and then this test particle, what will be the fate of that test particle? Injected it through some window, and it went in, and it collided to another particle in the gas, which is here in equilibrium. And that collision has to be, like I told you, has to be head-on. So two particles will collide, and then they will scatter sideways somewhere. So the other way. They will scatter sideways. Then, as a result of this process, I mean, these states will no longer be populated, but this state will now carry a Hall, because that particle, if collisions wouldn't happen, this particle would continue here and would come out here, and now it doesn't. So the state will carry a hole. So the picture, the real space picture is that there is this particle to hole conversion in the zigzag, zigzag particle forward, hole backward, kind of like the Andreev scattering. And then this hole, of course, can collide with another hole and retro-reflect, and so the particle will scatter to hole and the hole into particle, and will, go back and forth like that. I mean, we'll get to that later if we want to. But that's basically the real space picture. So it'll be. I have some good picture down in the talk. Show it later. Any other questions? Yeah.
How did you calculate this for internet or parity excitation? You use the Purvis-Golden rule to calculate that? Like
Pretty much. Yeah, I'll talk about it actually, how much time I have. Half hour. It's a lot of time. Wow. Okay. Yeah. Okay. Good. So we'll get to golden rule in a bit. Yeah. But I mean, before we actually, why am I showing this? So maybe the reason I'm showing it is that I'm going to spend some time, maybe in 10 minutes, I'm going to spend some time talking about what you asked, how you calculate these things. But what I want to do now is to, like, anticipating what comes next, is to show a route to observables. I mean, show that if you, let's say, if you calculated, analyze these collisions and calculated lifetimes for these different harmonics, then you can convert it into observable. And there is a pretty general way to do it. And I should have done it on a chalkboard, but I think it's most of it is pretty elementary. So I just copied and pasted equations from paper on the slides. You can follow the kinetic equation. I mean, you can probably do it diagrammatically. Actually, you can do it diagrammatically, but because we're interested in kinematic effects, I think it doesn't really matter whether you do it by one way or the other. And in this way, it's much simpler. I mean, also non-trivial, as you will see, but much simpler. So let me do it using kinetic equation. So we start with the Hamiltonian for usual Hamiltonian p square and u of r will be, let's say, potential of an applied electric field which drives current, and we want and we have electron collisions, and we want to derive conductivity with full account of these harmonic rates, right? So what do we do? We start with kinetic equation, and that thing is Poisson bracket of my distribution function and the Hamiltonian. And if I calculate, I'll get what we're supposed to get, the right-hand side of kinetic equation, and then put it in, and then apply an electric field, DC or AC, and then calculate perturbed current distribution. Say applied electric field varying at some weight number and some frequency, calculate current distribution, calculate distribution function, and then compute current, and that gives conductivity. And so in doing that, it's convenient to take the distribution function, and that's a beginning to answer your question. Take the distribution function, which is a general function, and as a general function, it can be decomposed in angular Fourier series, like so. So these are not some special shapes, these are just Fourier harmonics, which are valid for, which can be introduced for any function, and these are coefficients that will be amplitudes of population of these different harmonics. So you can do that, and then you can take that and then combine with this equation and try to derive evolution equations for these guys. Easy enough to do. Because this is an interacting system, you need to be a little careful with screening, but I mean, let's not get into that because it all can be done, and it's on a paper to which I refer, but it's not going to be of any importance. So anyway, so you decompose in the angular harmonics, and then after you've done that, you look at the collision operator. So collision operator, as you said correctly, is just a golden rule for scattering from two states to other two states and back. And so we have to write it carefully, and we can write it in full glory. This will be an interaction matrix element, and populations of the incoming states and outgoing states, and then these will be kinematic constraints for the energy. Two particles coming in, total energy doesn't change, and momentum. Two particles coming in, total momentum doesn't change. So we do all that, and then for this linearized, interaction can be anything. I mean, if you want to do it with short range interaction, that's fine. If you do it with Coulomb interaction, that maybe even better. Qualitatively, it's not going to be important, because we're not saying that it's the interaction that which produces scattering forces particles to go in a particular direction. And interaction can be fully angle blind, or maybe not so angle blind, Coulomb interaction is, but it's not going to matter. It comes from kinematics, not from interaction. So if we do that and start solving kinetic equation, then solution, what textbooks recommend is to look for solution of linearized kinetic equation using this Engskog ansatz. Because if you do that, then your kinetic equation, which is fairly complicated, starts looking much simpler. So your collision operator in this parameterization can be written in an additive way in terms of these quantities. And so now you switch from changing the distribution function to changing these etas, and you do the same thing. You do angular momentum decomposition, and then you expect to find a solution in which these different harmonics relax in different rates, with different rates. And these are the rates that we're interested in. We can find these rates. We'll find these rates later. I mean, in 5 minutes, we'll find those rates directly from direct diagonalization. But if you just let me assume that there are some rates here that I get, which are telling me at what rate these different harmonics, even parity and odd parity, are relaxing in time, then they'll be here. They'll contribute like that in the general solution. And if I do that, I mean, the rest is fairly easy. You just need to combine that Fourier decomposition and everything else, and put it in the kinetic equation. I mean, you also need to do some algebra and express the field term and the streaming term in terms of angular harmonics, and that's fairly easy to do. Then after this is done, you pick up your kinetic equation becomes a linear relation between coefficients of different between angular Fourier coefficients of different harmonics, and it will look like so. And the structure, the tri-diagonal structure, comes from streaming terms. So streaming term, go back to kinetic equation. Where's my, so if you go back to kinetic equation, where there is the streaming term. So the streaming term is an in product over vector in momentum space and vector in coordinate space. And so it's, if you write it in angular harmonics in momentum space, there will be terms with cosines between P and R, right? And then these cosines, if you go to Fourier representation, they generate these shifts of m plus 1 and m minus 1. So the kinetic equation, if you write it in the strange representation in terms of angular harmonics, will become a tri-diagonal system of equations. And then these equations you can solve because if you if you just take that, sorry, it's a little quick, but I think I'm not hiding anything. Take that, then your electric field, which is driving current, it appears as a source term on the right-hand side, and that source term, because of the angular dependence of field-dependent term, has only m equal +1 and m equal -1 components. So this source term has m equal +1, m equal -1. So these are free equations if m is not equal ±1, and if it's ±1, then there is a source term proportional to electric field harmonic, given explicitly here. And so then this problem, I mean, as many of you I'm sure know, can be solved by continued fractions. I mean, you can introduce ratios of adjacent of m and +1 amplitudes, and then for these ratios you can rewrite the equation we had on previous page as an equation between m ratio and m-1 ratio. And then these look like recursion relations that if you iterate them, you just get continued fractions, and you can express distribution function as a continued fraction of all these harmonics that we have in this problem for relaxation rates of different harmonics. And so in this way you can derive. I mean, I know it's long and elementary, so that's why I didn't want to do it on a chalkboard. But you can probably trust me. You can derive this general equation for non-local conductivity, that relates for an arbitrary wave number and their arbitrary frequency, relates the current field response to these lifetimes of different harmonics. And twiddle means that we're doing it at constant frequency, and we changed gamma m to gamma m minus I omega. But that's not going to be important for us. Anyway, so you can derive this general relation, and totally as general as it can be. And then because it's so general, you can apply it to many different situations and have fun exploring it. I mean, obviously the simplest case to study is when these rates are all the same, except that momentum, except gamma 1, which is momentum relaxation rate. So I can take momentum relaxation rate to be something, and then these electron-electron collision rates to be something else. And if I take them to be the same, which isn't correct, by the way, because we know that the even parity ones and odd parity ones are going to be very different. But if I, just as an exercise, take them to be the same, then this infinite part of continued fraction is very easy to evaluate. You can do it back on the envelope, and then you get a closed form expression for conductivity, in which you can, when the wave number is equal to 0, it agrees with the Drude conductivity. But if momentum relaxation rate is equal to 0, then you get the conductivity response that you would otherwise get from diffusion equation, linearized diffusion equation. And so in this way, you can connect it to diffusivity of the selection system. Of the general. Anyway, I'm showing it not just to brag, but to emphasize that if you know these rates, and when going to look more closely at these rates, then you know a lot about the system, including conductivity as a function of k and omega, and everything you want to know will be encoded by this gamma m. So that you can say that they're playing a role of a genetic code of the system. And if you know these numbers, then you know a lot about the system. And so that's the end of that story. And maybe. Yeah, maybe. So this was like to demonstrate that theoretical physics is useful for something. That if you know these eigenvalues of your linearized collision operator, you can actually learn something about observables. But then we're not doing it for the actual case of interest yet. But anyway, let's see if there are any questions. Yeah.
So why gamma p equals 0 leads to electron loss?
Oh, because sorry. So there are, yeah. So the question was, I mean, there are these gamma m rates of relaxation for the angular harmonics. Let me go back to the picture of angular harmonics and use that to talk about that. So m equals 0 harmonic corresponds to density change, right? You can see it graphically from here. So if we are in a particle conserving situation, then that will not relax. That will be protected by particle conservation. So we expect gamma with m equals 0 to be 0 if particles are not relaxing. If a particle number is not relaxing, sorry about that. Now, m equal 1, similar. If momentum is conserved in collisions, we don't expect that to be relaxing, unless there is momentum non-conserving processes like disorder of phonons. So there will be no electron-electron contribution to these relaxation rates. And if particles are not disappearing or not being added, then that will be protected. And then that generally isn't protected if momentum is not conserved or momentum is not conserved because of collisions or because of phonons. So electron-electron interactions are blind to these relaxation rates, but yeah. Sorry, the other way. Electron-electron relaxation rates are blind to these relaxation rates, but not blind to these other rates. Does that?
Yeah, I'm just trying to understand the connection between M and the gamma M. So what's the meaning of this gamma M connection? These different channels.
So gamma M is the rate that we will find from linearized collision operator. Basically, will be a rate at which memory will be lost in that harmonic. But nothing will happen to the harmonics that you pointed to. Nothing will happen to m equal 1, m equal 0 because momentum is conserved, particle number is conserved. Yeah. More questions? Yeah.
So you can actually teach the 4 rates.
Hmm?
You can either teach the 4 rates, relaxation rates of auto harmonics in an experiment.
Is it seen? Let me think. So there are experiments, sure. Has it been? We'll talk more about experiments later, but from all I know, there is nothing that is against that. But even, I mean,
One
yeah.
thing I worry about is that this is a bit of a linearized analysis. So, you know,
Sure. But I mean, okay, we'll get to experiments and how much they are say. But maybe at this point, I mean, just let's appreciate just as a theoretical problem because we are, we're discovering something interesting about two-body collision operator, mathematical structure of two-body collision operator, how its eigenvalues behave depending on how blurred the Fermi surface is, and regardless of what experiments do, I mean, we should pay attention to that, but that's of interest on its own right.
Yeah, but maybe even on the theoretical side, so that the relaxation rate of these odd harmonics.
Yeah.
I mean, at finite temperature, there will be thermal fluctuations that will couple these odd harmonics to nonlinear combinations of the conserved harmonics even.
Yeah.
And so that will lead to actually power law, right? Hydrodynamic tail, power law, decay, which eventually will beat these exponentials.
So something will, sure, yeah. But I mean, are you saying that these will be the dominant?
Well, late time certain.
I'm sure there will be contributions like that, but I mean, I'm not yet ready to agree that these contributions will overwhelm T to the 4th. I mean, thought a lot about it, but can discuss later. Okay, let me just show you one more bit, depending on how patient we are. Oh, okay. So let me show you this because this is fun. Because this is fun, and it's something totally unexpected that I learned doing this work. So one can ask, and actually people asked a long time ago, can one, if we are trying to if we're trying to study this linearized collision operator, here we derived it earlier, but here it is again. Same thing as before. I mean, these in this N-squared parameterization eta additive combination, and then these are occupancies of in and out states, and this is interaction matrix element. So I'm up to linearize this collision operator. Can I do it by doing something like Sommerfeld expansion, careful Sommerfeld expansion near the Fermi surface? I mean, we always do Sommerfeld expansion for when we calculate specific heat and so forth. Can we do it for this problem? So people thought about it, and we can also try that route, and we'll discover something interesting. Just bear with me for a minute. So we can focus, just like before, we can focus on individual angular harmonics and take that and plug it in linearized eigenvalue equation, and then we'll get a linearized eigenvalue equation in which this gamma m that we're looking for will play a role of spectral parameter, and so we'll get an eigenvalue equation that will look like that. This will be equilibrium distribution function. These will be eigenstates, and so there will be this problem that we need to solve, and so that this equation I can rewrite as people did long before us. I can rewrite the time-dependent equation. I can write down as an equation for relaxation in each individual angular momentum channel, and in that channel there will be angular average of there will be an angular average of these guys over spherical harmonics or angular harmonics, and it will look like that. And then from that angular average, you'll get the t-square, as inevitably as always when you're doing Sommerfeld expansion, you'll get a t-square as a prefactor, basically because of what you said, because of fuzziness of the Fermi C. So naively, when you write it like that and you say that time derivative proportional to t-square, you expect that all eigenvalues will scale with t-square. And as a matter of fact, they do in 3 dimensions. In 3 dimensions, you can do exactly the same analysis, and then you can see that all eigenvalues are for different harmonics. I mean, they have different coefficients, but they all scale as t-square. And so from Boltzmann point of view, or from Landau point of view, the eigenvalues lambda will look like that. I'm not sure. Yeah, so they will form. There will be two degenerate ones. There will be 2 eigenvalues, zero eigenvalues that will correspond to momentum and density mode, and they will be Weiss degenerate. And then all other eigenvalues in 3-dimensional Fermi liquid, they will be somewhere here. I mean, they'll have different coefficients, and all of that will scale as t-square. So this is how 3D Fermi liquid looks like. And this is well known. I mean, we can references in that paper, and I'm sure you'll believe it right away. But what maybe is less well known is what these people did. So what they discovered is that if you take this linearized equation, which you just write mechanically by doing Sommerfeld expansion, no magic, then if you take that and you for whatever reason, I have no idea what guided them, but you change variables, and instead of energy variable, you introduce a conjugate variable, do Fourier transform in the energy variable on this equation. Then if you do that, I mean, you might think that it will become even more horrible. So this is the integral differential equation, and it looks pretty horrible. It has delta functions in the kernel and whatnot. Multidimensional, looks pretty bad. But they found, I don't know, no idea what guided them, that if you do this transformation in energy variable, Fourier transform energy variable, then rescale your variable like so, then you get in each angular momentum channel you get one-dimensional supersymmetric quantum mechanics problem with hyperbolic function potential, and so that by itself is pretty interesting. So-called Forshall-Teller problem, which is pretty interesting by itself. What's even more interesting is that Forshall-Teller problem is exactly solvable, and so in this case you can find all eigenvalues exactly. Again, and they used it. So these papers used it to actually invert linearized collision operator, which they had to do to describe viscosity of a Fermi liquid, which in their case was helium-3 Fermi liquid. And so using that trick, they were able to describe very accurately viscosity and thermal conductivity and other kinetic coefficients of helium, basically using this trick. I mean, inverting it by doing that transformation and then solving this equation, which can be done explicitly. So this is pretty striking, and yeah, I mean somehow that line didn't continue in the literature, even though it looks super interesting. I don't know what was the story afterwards. I haven't found any publications. But what one can do is apply it to 2D system. I mean, in 2D system, one gets exactly the same story, except that coefficients change and something else changes. But one gets exactly the same story, and it turns out that the coefficient of 1 over cosh changes, and in 2D, you get quantum supersymmetry one-dimensional problem that you can solve exactly, but in addition, you find that there is a zero mode, one for each odd m, one for each odd m channel. So in this case, you prove that your problem, that your eigenvalues here, they actually don't have a gap separating the ones which are mandated to be zero by symmetry and the one which are not mandated by symmetry. So this gap closes, and there are some low-lying eigenvalues, one for each angular momentum, so infinitely many for each odd angular momentum, and that's a mathematical statement for linearized collision. I mean, pretty interesting to me. It also shows that at order t square, because there are these zero eigenvalues, I mean, there are no relaxation for odd m harmonics at order t square. So it has to be higher power of t, higher power of temperature. And if you ask me, and I'm sure someone will, what's the energy dependence for the zero modes? It's very simple. If you do reverse engineering, that converts to what you would guess naively df d epsilon for the equilibrium distribution. So the details are here, and yeah. So basically, what you conclude at this stage is that there are, like we said, there are zero modes, one for each odd m. And when you're doing this calculation, you see explicitly that for odd m, there are zero modes. For even m, it's like in Landau Fermi liquid at t square. And so there is no, in general, there is no gap between these eigenvalues, which normally are t square, and the zero energy ones. Here they all occur at low at low value. And that means that there are many abnormally long-lived excitations. So we need to study, exactly how long-lived and what are the memory times and so forth, so forth. And so from the general point of view, that's a pretty interesting behavior because it signals that there is a breakdown of the usual Landau's T-square kinetics and ergodicity at 2D Fermi surfaces. Yeah. So maybe then the last bit, if I still have, do I have 5 minutes?
About 2 minutes, so that we have.
2 minutes, sure, yeah, 2 minutes. So what one can do to actually look further into it, one can take that linear collision operator and diagonalize it on the computer. Forget about doing something analytically, forget about supersymmetry. Probably there are also things that can be done using analytic tools. We tried to make progress, turns out harder than we thought, but one can simply put it on a computer, introduce grid, diagonalize it, and then you see that indeed eigenvalues as a function of temperature behave as you anticipate. In angular momentum, in even angular momenta, you see T-square scaling. In odd angular momenta, you see something which is close to T⁴ scaling. Then later people redone what we did more accurately, and you indeed see pretty accurately T⁴ scaling. So that's maybe the end of that part of the story, and I think that's all for today. Maybe let me just see what this says. I forgot what I wrote here. Yeah, no, it just summarizes what we said. So there are long-lived excitations, abnormally long-lived excitations, scaling much slower, much differently than Landau scaling predicts, and at the same time there is a conventional Fermi liquid scaling for all even M harmonics, and that's the story. And then we'll have to wait to discuss why it's tomographic and all of that, so that will come out next. But maybe let's stop and see. Maybe to conclude is that there is what we're discovering is that there is a wide hierarchy of timescales. There are timescales. There are Landau type timescales, T² timescales, 1/T² timescales, but then there are also much longer timescales due to higher powers of modes with higher powers of temperature. So 2D Fermi gases are more complex than 3D, and that's quite rewarding to see. Yeah. Anyway, so let's stop here. Yeah.
The numerics, why do you have deviation from T⁴?
Why do we
You
have?
have deviation from T⁴, you have 3.3.
I'm just showing our results from the first paper. Later people done it more carefully, and they saw. So basically, when you do it numerically, you can go to very low temperature, because when temperature becomes very low, your thermal distribution becomes very thin, and it's very hard to sample it. So you have to stop somewhere where you sample, and because of that, here we went to temperature which was low but not too low. It was only like decade below Fermi energy. But then if you can go even lower, then you see T⁴ was better.
So presumably, transport in resistivity is dominated by the fastest relaxation time. That's Matheson rule still works for transport.
Some things will be dominated by fastest. Some things will be.
So it depends on the experiment.
Depends on what you're probing. There are some things which will be sensitive to.
In conventional transport, what is it in conventional transport?
In conventional transport, to begin with, we usually measure K = 0 response. We measure response of uniform current to uniform field. So all of that is a finite K effect. So we'll see nothing at all. But if we're interested in viscosity is a wave number effect, because viscosity only arises if you have a shear flow, if you have
But then it depends on
non-uniform system, and then you are directly sensitive to all of that.
But the idea is somehow to prefer an excitation which is odd M. To think of an experiment where
Yeah. So that's next. That's what I am going to talk about next. Yeah.
What happens from the crossover, like from small temperature to bigger temperature, like this dome, right?
Oh, so at high temperature, you go to classical gas. You lose Fermi statistics effects completely. I mean, you get exactly what Maxwell would have predicted without knowing about Fermi statistics. Because Maxwell wrote, Boltzmann wrote it for classical gases and could have done this analysis. And for classical gases, I mean, we know collision rates. It goes as 1 over square root temperature, or 1 over temperature, something like that. And so that's what that is. Yeah, there was another one. Yeah.
So, can you get this from diagrammatic theory? You basically tell the energy, right? That this T square is still the imaginary part of the cell energy, right? Can you get this T to the power 4 for all?
Diagrammatically, I think so, because I mean, what diagrams do for you, they just give you letters, and letters are well known to sum up to linearized kinetic equation. That's that's textbook.
You get T to the power 4 or
So we ourselves looked at what I told you. I mean, the relation between ladder diagrams and linearized kinetic equation is well known. I mean, the paper along these lines is what how you worked on, and I think I'm not sure if he did it for Fermi liquid, but for non-Fermi liquid there is something similar, right? Yeah.
a question about your introduction. You show the figure where the conductivity increases like with increasing the temperature, right?
Yeah.
Is that the sharp feature of the tomographic fluid?
Well, that's okay. Good question. Can you explain it in a non-tomographic way? We don't know, but it comes out in this way. It comes out naturally.
So I also remember that the Kondo impurity problem also have this feature. The Kondo impurity problem.
Oh yeah, Kondo. Yeah, mentioned that. Yeah.
So is this in this case kind of one side of the Kondo impurity problem, the strong Fermi liquid phase, strong correlated Fermi liquid phase, is also the tomographic electron fluid.
Yeah, but I mean, so the systems. I mean, we can discuss the systems where these experiments are done. I mean, there is absolutely no reason to suspect that there are localized spins there. I mean, just not any of the kind. I mean, we can maybe not now, but we can talk about it later.
Should one be resumming over these channels? Like, is there,
To get what?
I don't know, to get, is it a divergent series or is it some kind of a series that, is it a convergent series?
I mean,
coefficient?
probably depends on the quantity. I mean, maybe some like for Eisenstein, it doesn't matter because he is measuring the lifetime, the cumulative lifetime, and that's dominated by even channels. But someone probes something else, then there'll be other things to worry about. Okay, looks like we're done. Yeah, good. Thank you.